Okay, hi everyone. I'm very happy to be there today to present to you GraphUnzip, which is a software that I've developed in the Université Libre de Bruxelles with the help from Nadège Guglielmoni and Jean-François Faure. So GraphUnzip unzips assembly graphs. To understand what unzipping assembly graph means, let's go back to the process of genome assembly. So the first step when you're trying to recover the DNA sequence from an organism is to sequence the DNA strands. However, the difficulty is that we do not have any technology able to sequence the strands from the chromosome from one end to another in one go. We only have technology capable of sequencing very short fragments of DNA. And that's why the computational assembly step is needed afterward to align all those small fragments and assemble them back together into long sequences that we call contigs. As you see on this slide, when you have a sequence present several times identically across the genome, like the red sequence here that's homozygous, so present identically across both haplotypes, the assembler does not really recover the original haplotypes. And that's the meaning of the bottom of the slide. You see that when we assemble the genome, we got an assembly graph, which can be read as before the red contig can come either blue contig, and after the red contig can come either green contig. But from the assembly graph, we cannot recover the original haplotypes because we don't know if the dark blue sequence here is on the same chromosome as the dark green sequence, or is it on the same chromosome as the light blue sequence. Sorry. We're in this situation because there was no reads at the sequencing step that span both blue and green sequence. So I'll show you what an assembly graph looks like on a real animal, which is, so I've taken the example of Adenta vaga, which is a small animal with 6 pairs of heterozygous chromosomes, and on which we had PacBio sequencing to assemble the genome. So here we go. You see that we're quite far from having recovered the 12 original chromosomes. We still have many contigs. So from the assembly graph, there are several strategies to try to finish the assembly. The first one is to output to the biologist directly the contigs as they are represented in the graph. The problem of such a technique is that you output very short contigs. The outputted assembly has very low contiguity, which makes it much harder for the biologist afterward to analyze it. And another problem is that some of the contig you output, like the dark blue contig, is present once in the original genome, while other, like the red contig, is actually present twice in the original genome. And that makes the analysis harder too. The second strategy you can do is to collapse the assembly graph. Collapsing the assembly graph means that each time you have a choice between two contigs, you have a choice between two blue or the two green contigs, you choose one and you discard the other. This has the advantage of yielding very highly contiguous assembly with very long contigs. You see there that we recovered the contig that was the length of the original sequence. But the problem is that we collapsed the two original haplotypes into only one sequence. And that means that we lost information. You see that on this example, I've discarded the light blue contig, for example, and so I've lost this information. And moreover, since you obtain a sequence that may not actually exist in the actual genome. Here I've discarded the light blue config and the dark green config, which deal with a sequence that does not exist. There is a mix between the two original prototypes. The last strategy you can do, and the most precise one, is to unzip the assembly graph. Unzipping means duplicating the right contigs and associating the right contigs together to recover the original prototypes. But as I've told to you before, this is difficult because from the assembly graph, we have no way to know what are the original haplotypes. Is the dark blue config associated with dark green config, or is it associated with the light green config? So to solve this question, there is the need of additional data. And so GraphUnzip, the software that I'm presenting to you today, is precisely a software capable of unzipping an assembly graph with the help from additional data. And to the best of my knowledge, it's the first software able to do that. The first type of data we can use to unzip the assembly graphs is high-C data. So I'm not going to go today with you into the precise working of high-C, but what you need to know is that you can measure high-C contact frequencies between contigs, and that these high-C contact frequencies have two very interesting properties for us. The closer two contigs are, the more frequent are the contacts between them. And secondly, contacts between two contigs that are on the same chromosome are much more frequent than contacts between two contigs that are on different chromosomes. And on this slide, you see an illustration of the high-C contact frequencies of the dark blue contig. So very high with neighboring contigs and much lower with contigs that are farther away or on other chromosomes. So with that, if we look at the high-C contact frequencies of the blue and the green contigs, we can guess the right unzipping. Because if there are very strong high-C contacts between dark blue and dark green contig, we can guess that they're on the same chromosome, while there are very few contacts between dark blue and light green contigs, so they're probably not on the same chromosome. So it's possible to use this information to unzip the graph. Another type of information we can use to unzip the graph is very long reads. If you have reads that are long enough to span several heterozygous regions, you can map them to a graph using graph aligner, and then you can use it to unzip the graph. Very simply, if there are a lot of reads aligning to the dark blue and the dark green sequence, and no read aligning to the dark blue and the light green sequence, we can guess that the correct unzipping is to associate the dark blue and the dark green sequence. So now I'll show you the algorithm of GraphUnzip. So it iteratively look at the alternative path in the graph. So here it starts with the orange star, and each time it looks at the high-C contact frequency between what's left and what's right of the star. So in this case, there is a very high-C contact frequency between the black and both blue contigs. So GraphUnzip guesses that the black config is next to both blue config in the real genome. It can do the same reasoning with long reads. If a lot of long reads align to black and dark blue, and a lot of configs align to black and light blue, GraphUnzip guesses that the black config is next to both dark blue and light blue in the original genome, from which we can deduce that we need to duplicate the black config. GraphUnzip then moves on to the next alternative path, here once again represented by the orange star, and looks at the high-C contact frequency between what's left and what's right of the star. So the red config has high C contact frequency with both dark blue and light blue config. So we can guess that the red config is next to both blue configs, and we duplicate the red config. The algorithm continues. GraphUnzip looks at the next branching here, but this time the situation is a bit different. The dark blue config shares a lot of contacts, well, many contacts with the dark blue config, so that's probably on the same chromosome, but shares very few contacts with the light blue config, which means that they're probably not on the same chromosome. And from that, GraphUnzip deduces that it needs to delete the path going from the dark blue config to the light blue config. And it deletes it. Okay, it moves on to the next branching, and once again, there are no high C contacts between the light blue and the dark blue config, which means that they're probably not on the same chromosome, and the path is deleted. Still moving on, it looks at the high C contact frequency between the ground config and the two possibilities. And once again, there is a very high C contact frequency, which means that the ground config should be duplicated. And here we are. We have unzipped our graph. So let's just see what it looks like on a real example. So in the Identita Vega example that I've already shown you, at the left of your screen you have the assembly before GraphUnzip, and the right of your screen you have the assembly after GraphUnzip. To evaluate how well it worked, we measured the assembly size, because since GraphUnzip duplicates config, we expect the assembly size to rise, and we see that it rose exactly to the size that we expected for deployed Identita Vega. We also measured the N50, which rose from 340 kb to 2 megabase per, meaning that more than half the genome after unzipping was contained into contigs longer than 2 megabase per. Here is a little graphical zoom on the unzipping of Identita Vega. So before unzipping, at the top of your slide, there was a zone with clearly two haplotypes that were with heterozygous regions and homozygous regions. And GraphUnzip unzipped that into two long contigs. Some other results from the proceedings. So human at the top and potato at the bottom. You can notice that when you have both very long reads and high C to unzip the graph, you can use either or both together. And often the best result comes when you use them both together. Another thing that's worth noticing is the very low runtime and CPU usage of GraphUnzip, which is really nice, and you can even on many assemblies, depending on the size, you can even run it on your laptop. So it makes it quite easy to use. You noticed when, after the unzipping of Identita Vega, that still we did not recover the 12 original chromosomes. There was still a bit, we had more context than that. And that's because of what you see left of the screen. It's because in many assemblies, we have regions that are very complex with very small context. And the problem with small contigs is that high C data does not map on them very often, and so GraphUnzip is blind in this zone, and it has to stop unzipping that. A second limit of GraphUnzip for now is that if for some reason an edge is missing in the assembly step, so here to take the example we already had before, with a missing edge between dark blue and red config, then GraphUnzip will duplicate the light blue config to associate it with both green config, and we will have three triploid assembly, which is not what we expect, and the error will be propagated. So we're working on making GraphUnzip more robust to that, but there's still it might still happen in some cases. So to sum up, GraphUnzip is the first software to unzip assembly graphs, and it can use either high-C or long reads or both to do so. It's available on GitHub, on the GitHub of Nadej. And on that, if you have any question about the GraphUnzip, please ask them.
Thank you, Roland, for your nice presentation. The sound is not really good, but I hope everybody can hear you fine. So we have a first question from Matthias. He says that in the example you provided, you specifically compare the blue context with the green one. How do you choose the pairs of context to compare? Do you get back to the different context, itself, or part?
Yes, yeah, thank you. This is a very interesting question. So here, at this step of GraphUnzip, you notice that I compared the blue and the green contigs, and that's because GraphUnzip remembers which contigs were duplicated, so in this case, the red contigs, and does not use them to compare the strength of the high C contact frequency, because you can see that the light green config is next to a red config in the actual genome, so it would have very strong high C contact frequency with the red config. So it does not take into account the configs that have been duplicated. It only uses the configs with that are unique to each long super config.
We have another question. Like, want to know whether we have another criteria than history to evaluate the quality.
Yes, we tried other things too. Another thing we tried was the Busco score. So it's the gene that you expect to see in the assembly. And so you can measure if you saw them once or twice. Because in a diploid assembly, you expect to see them twice, while in a collapsed assembly, you expect to see them once. And there, once again, we saw that there were many Busco features that were duplicated. So it means that well, the homozygous region were widely duplicated in this case. Thank you, Nadej, for your question.
We have another question from Roland. Have you tried to compare it with Hi-Fi ASM haplotype resolving algorithm? No,
we didn't for now.
I think there's another question in the direction. Did you test your tool with another sample than Hi-Fi ASM? Without SMB?
Yes, we and actually, the example I've shown you on Avineta Vaga, this example was assembled using the regular pack dial reads with Shasta, with the assembler Shasta. And so in theory, you can use any assembler. But yeah, the constraint is that the assembler needs to output the assembly ground, while some assemblers still don't.
We have a chance for another question from Fabrice. How does your deal with changes on plasmid for bacteria as decided?
So yes, we've tried it, and well, no, sorry. Sorry, I haven't read properly the question. We haven't tried it, especially with phages and plasmid, but we did try it on a simulated bacterial genome with several haplotypes. And yes, it can also separate haplotypes for bacterial genomes, theoretically, if you have a good data on that. And well, if you have high-C data or long-read data that is available for plasmid or phages, there is no theoretical reason why it shouldn't work, but we haven't tested it.
Okay, maybe one last short question from Eva. Could you replace Superpool replace tools as upload builders?
Yes, I've seen this question. Sadly, I'm not really sure of what HubCommerce does, so I can't really answer this question. Sorry.
Thanks a lot for your answers and your presentation. And here,
Well,
that
thank you.
we have the coffee break. And thanks a lot, everybody, for joining us.